November 1st, 1755. Without warning, the city of Lisbon was erased by waves so powerful they wiped out entire coastlines. All triggered not by the Pacific, but by a fault line in the Atlantic. Today, just off Puerto Rico, a trench 6,800 meters deep has lain silent for 8 centuries, storing tension inch by inch. Scientists now warn that this underwater giant could unleash the deadliest tsunami in history, with Caribbean shores left just 15 minutes to react. Few realize the evidence buried beneath our feet proves the risk is real. What exactly is building beneath the Atlantic's surface? At the heart of 18th century Europe, the city of Lisbon woke to a day of celebration. It was All Saints' Day, November 1st, 1755. By mid-morning, the ground began to convulse beneath the city's cobbled streets. Eyewitnesses described the earth heaving like the sea, buildings collapsing in seconds, and crowds fleeing toward the open waterfront, desperate for safety. But the true horror had not yet arrived. Out in the Atlantic, the sea receded. Some said it vanished, leaving ships stranded on the riverbed. Then, without warning, a wall of water swept ashore. The first wave engulfed the harbour, tossing ships into the city and smashing what little remained of the riverside markets. In the words of one survivor, the sea itself rose up and devoured the living. Within minutes, tens of thousands were dead. The waves spread outward, battering the coasts of Spain, Morocco, and even distant islands. In Lisbon, fires raged for days, erasing entire neighborhoods. The Marquis of Pombal, charged with the city's recovery, recorded the devastation in his official reports. Churches leveled, palaces gutted, and entire families lost to the sea. The event sent shockwaves through Europe, not just physical, but intellectual. Philosophers and scientists struggled to explain the scale of the destruction. The Atlantic, long considered a quieter ocean, had revealed its capacity for sudden, unimaginable violence. For centuries, the Lisbon disaster stood as a singular warning, proof that the Atlantic could unleash tsunamis as deadly as any in the Pacific. Engravings from the period show a city transformed into a wasteland, its people left to count the cost of a catastrophe no one thought possible. The memory of that morning and the waves that followed lingers in the historical record, a reminder that the threat beneath the Atlantic's surface is neither distant nor forgotten. North of Puerto Rico, the Atlantic seafloor plunges into darkness. The Puerto Rico Trench stretches for nearly 800 kilometers, its floor reaching depths of 6,800 meters, deeper than anywhere else in the Atlantic. This chasm is not just a line on a map. It is a boundary between tectonic plates, an active subduction zone where the North American plate slides beneath the Caribbean. The trench runs frighteningly close to inhabited shores, with some points lying less than 100 kilometers from San Juan. Scientists at the Puerto Rico Seismic Network spend their days tracking tremors along this boundary, watching for patterns that might signal a coming rupture. But the story of the trench is written not only in seismic records, but also in the layers of earth along the coast. Over the past 2 decades, geologists have drilled deep into coastal ponds and caves from Puerto Rico to the Virgin Islands. Their cores reveal abrupt, basin-wide layers of sand and coral fragments, deposits that appear out of place, far from the normal reach of waves. Radiocarbon dating pins these layers to between 1200 and 1500 CE, centuries before the arrival of written records in the region. At East Bajura Pond, a thin sheet of marine sand lies buried beneath centuries of mud, its mineral signature matching the open ocean. On Anegada, in the British Virgin Islands, coral heads and marine sand are found hundreds of meters inland, carried there by a wave of extraordinary force. The evidence points to a prehistoric tsunami, one that swept across the northern Caribbean with enough power to move coral boulders and blanket entire ponds with ocean sand. These layers are continuous, sharply defined, and chemically distinct from hurricane deposits. Microfossil analysis reveals marine species transported far inland, while grain-size studies show the rapid, high-energy flow characteristic of tsunami inundation. The inland reach, often more than 500 meters from the shore, rules out storms as the cause. All signs indicate a single catastrophic event, likely triggered by a rupture of the Puerto Rico Trench. For scientists, these ancient deposits serve as both a warning and a map. They confirm that the trench has generated massive tsunamis in the past, and they allow researchers to estimate the frequency and scale of such disasters. The last major event, now dated to more than 800 years ago, suggests that the region is overdue. Each new core drilled, each layer catalogued, adds detail to a portrait of risk that is no longer theoretical. The threat is real, measurable, and alarmingly close. Along the edge of the Puerto Rico Trench, 2 tectonic plates are locked in a slow-motion collision. Each year, the North American plate pushes toward the Caribbean plate by about 3 to 4 centimeters, the width of a finger. On the surface, this movement is invisible, but beneath the ocean floor, the plates are stuck. Friction prevents them from sliding smoothly. Instead, strain builds up, year after year, like tension winding in a spring. Geophysicists use GPS stations anchored to bedrock across Puerto Rico and the Virgin Islands to measure this relentless movement. The data show a steady convergence, unchanged by centuries of apparent calm. Over 8 centuries, this rate adds up. 3 centimeters per year means 24 meters of potential slip have accumulated since the last known megathrust event. That's the length of a city bus locked in place, waiting to be released in seconds. This is not a theoretical risk. The same mechanics drive the world's largest earthquakes and tsunamis. When the plates finally slip, the stored energy is unleashed all at once. The seafloor can heave upward by several meters, displacing vast volumes of water. The 800-year gap since the last full rupture is not a sign of safety. It is a warning. The longer the plates remain locked, the more energy is stored, and the greater the potential for devastation. Modelers describe the trench as a loaded spring compressed over centuries. With every passing year, the strain grows. The rupture, when it comes, will not be gradual. It will be sudden, violent, and unstoppable. The numbers, 3 to 4 centimeters per year multiplied by centuries, translate directly into the scale of disaster possible. This is the hidden arithmetic of catastrophe, measured not in days or years, but in meters of locked fault beneath the Atlantic. Coastal cities, unaware of the silent build-up, live with the consequences of this buried tension. Scientists track the numbers, knowing that each year without an earthquake makes the eventual release more severe. Half a world away from the Atlantic, the Indian Ocean bore witness to one of the deadliest natural disasters in recorded history. On December 26, 2004, a rupture nearly 1,300 kilometers long tore through the seafloor off Sumatra. The fault slipped up to 20 meters in places, lifting vast stretches of ocean bottom in seconds. The energy released was staggering, equivalent to more than 20,000 Hiroshima bombs. Entire coastlines vanished as walls of water raced outward, some waves reaching 30 meters high. Cities and villages across Indonesia, Thailand, Sri Lanka, and India were erased in minutes. More than 230,000 people died, many with little or no warning. The world watched in horror as footage showed the sea swallowing land, buildings, and lives with unstoppable force. 7 years later, another subduction zone, this time off the coast of Japan, unleashed its own fury. On March 11th, 2011, the Tohoku earthquake ruptured a 500-kilometer segment of the Japan Trench. The seafloor thrust upward by as much as 8 meters, generating tsunami waves that sped toward shore at jetliner speeds. In some places, the water overtopped seawalls designed for lesser storms, surging inland for kilometers. The tsunami reached heights of over 10 meters, sweeping away entire towns and triggering the Fukushima nuclear disaster. Nearly 18,500 people lost their lives, and the scars, physical and psychological, remain etched across the country. Both events share a common origin: the sudden release of centuries of tectonic strain along a subduction fault. The rupture, length, and slip in each case determined the sheer volume of water displaced, and with it, the scale of the tsunami. These were not distant, theoretical risks, but real catastrophes, measured in lives lost and cities changed forever. The numbers: 1,300 kilometers of fault in Sumatra, 500 in Tohoku, translate directly into wave heights, run-up distances, and casualty counts. In both cases, the proximity of the rupture to densely populated coastlines meant that warning times were short and the devastation total. For scientists studying the Puerto Rico Trench, these disasters are not abstract comparisons. They are benchmarks, proof that a locked subduction zone, given enough time and strain, can unleash energy on a scale that defies imagination. The same mechanics, plate convergence, locked faults, sudden rupture, are at work beneath the Atlantic. The only difference is geography and the clockwork of human settlement along vulnerable shores. The lessons of Sumatra and Tohoku are written in hard numbers: rupture length, tsunami height, death toll. They serve as a stark reference for what could unfold if the Puerto Rico Trench releases its stored energy in a single violent moment. When a megathrust earthquake strikes the Puerto Rico Trench, the countdown begins immediately. Physics-based tsunami models, run by NOAA and academic teams, show how the seafloor's sudden movement launches a series of waves that race outward in all directions. In deep water, these waves travel at speeds approaching 800 kilometers per hour, faster than a commercial jet. The first shock of energy reaches the shallow shelf north of Puerto Rico in less than 10 minutes. San Juan, with its dense neighborhoods and crowded beaches, sits directly in the path. Maps produced by the U.S. National Tsunami Hazard Mitigation Program paint a stark picture. For a rupture along the trench, the initial wavefront would reach the city's shoreline in as little as 12 to 15 minutes. In some communities east of San Juan, the interval is even shorter. The models run scenario after scenario, changing the earthquake's magnitude, slip distribution, and rupture length. In every case, the outcome is the same. There is no time for mass evacuation. The Virgin Islands, Anegada, and the north coast of Puerto Rico all fall within the zone of near-instant impact. The wave height depends on the precise rupture, but even the most conservative forecasts show several meters of water surging onto land. For southern Florida, the timeline is longer, but not by much. Waves could arrive within 90 minutes, still too short for most emergency systems to mobilize. These propagation models draw on the latest bathymetric data, incorporating the trench's steep drop and the abrupt rise of the island shelf. The energy focuses as it approaches the coast, amplifying run-up heights and shrinking the margin for escape. The numbers are unforgiving. 15 minutes or less from rupture to inundation for the northern Caribbean's most populated shores. In the language of disaster science, this is a near-field tsunami, the most dangerous kind, where the warning is measured in minutes, not hours. On the ground, the reality of escape is shaped by concrete limits, roads, bridges, and the crushing speed of disaster. In Puerto Rico, the coastal plain narrows quickly into dense neighborhoods and tangled highways. The main arteries, PR2, PR22, and the bridges over the San Jose Lagoon are already infamous for daily gridlock. During an ordinary rush hour, traffic crawls, sometimes stalling for an hour just to cross a single bridge. In a tsunami scenario, with only 15 minutes before the water arrives, these bottlenecks become deadly traps. Traffic engineers from the Department of Transportation have run the numbers. Even with perfect coordination, the capacity of these routes cannot move more than a fraction of the coastal population inland in time. The same story plays out in the Virgin Islands, where steep hills and narrow roads funnel cars into single-file lines, with few options to turn or climb to safety. This is not just theory. On October 11th, 1918, a magnitude 7.5 earthquake struck off Puerto Rico's west coast. Minutes later, the sea rushed in. Archival newspapers and municipal death registers describe a wall of water hitting Mayagüez within 10 minutes, sweeping away entire families who had no warning and nowhere to run. Bridges collapsed, roads vanished under the surge, and survivors reached higher ground only by sprinting ahead of the flood. At least 116 people died, most within sight of escape routes that were already blocked or destroyed. City planners who study the event point to the same vulnerabilities today: critical bridges, low-lying intersections, and evacuation maps that look reassuring on paper but fail when every second counts. The lesson from 1918 is written in the casualty lists and the ruined streets, a warning that for many, the path to safety is cut off before the danger is even understood. Across the Atlantic, deep ocean warning systems have become the gold standard for tsunami detection, except in the waters north of Puerto Rico. The entire length of the Puerto Rico Trench remains unguarded by DART buoys, the very sensors designed to confirm a tsunami's size before it strikes land. NOAA's own records, updated through 2025, list 0 DART units positioned between Bermuda, the Bahamas, and the Virgin Islands. The nearest buoys in the Gulf of Mexico are too far to provide meaningful warning for a trench rupture. This absence is not for lack of trying. Over the past 15 years, NOAA has submitted no fewer than 6 formal budget requests to Congress, each one calling for a dedicated Atlantic DART array. Each time, the funds were cut or redirected, often with the justification that the Atlantic's risk was too low to warrant the expense. Internal budget documents from 2010 to 2021 show repeated attempts to secure $2 to $5 million annually for new sensors, requests that were either deferred or denied outright. Government audits have flagged the gap as a critical vulnerability. The Government Accountability Office labelled the Atlantic and Caribbean insufficiently monitored in reports from 2014, 2018, and 2022. Leading NOAA and USGS scientists have issued public warnings, citing the unique proximity of the trench to major cities and the impossibility of land-based sensors providing timely confirmation. Yet, as of today, the most dangerous subduction zone in the Atlantic has no direct line of defense. The technology exists, the risk is documented, but the sensors remain absent, leaving millions exposed to a preventable blind spot. Chile's coastline is lined with a web of sensors and deep ocean DART buoys, each one feeding real-time data to national warning centers. In Japan, thousands of seismic stations and a dense grid of offshore detectors stand ready to pick up the first hint of a rupture. When the Tohoku earthquake struck in 2011, alerts reached millions in under 2 minutes, and evacuation drills had already rehearsed the scenario countless times. Maps from the Japan Meteorological Agency and Chilean Hydrographic Service show dozens of dart buoys, and hundreds of coastal gauges, each forming part of an integrated shield. In both countries, earthquake and tsunami drills are routine. School children, commuters, and factory workers know their evacuation routes by heart. After the 2015 Illapel quake in Chile, sirens blared within minutes, and more than 1 million people moved inland before the first wave arrived. By comparison, the Atlantic is exposed. The Puerto Rico Trench, among the most dangerous subduction zones in the hemisphere, has no dart buoys stationed upstream. The sensor gap is visible on every global network map, a blank line where warning should begin. Annual Caribbean Wave exercises designed to test response times consistently reveal the consequences: delayed alerts, missed sirens, and confusion on the ground. After-action reports confirm that in many coastal towns, less than half the population reaches safety within the 15-minute window. The disparity is not due to lack of technology, but to choices made and priorities set. Where Chile and Japan treat tsunami readiness as a national imperative, the Atlantic remains vulnerable by design. The Puerto Rico Trench sits just 75 miles north of San Juan, reaching depths of 6,800 meters. Yet, it remains among the least monitored subduction zones in the Atlantic. Historical records confirm that the 1755 Lisbon tsunami killed tens of thousands within minutes, and sediment cores near Puerto Rico date a major tsunami event to between 1200 and 1500 CE. For over 800 years, the fault beneath the trench has been locked, accumulating strain at 3 to 4 centimeters per year. Models show a rupture here would send waves to Caribbean shores in under 15 minutes. Yet, as of 2024, there are no dart buoys positioned to provide real-time warnings for this sector. Scientists agree it is not a question of if, but when a major event will occur. What remains unknown is the exact timing and scale of the next rupture. As coastal populations grow and infrastructure lags behind, the evidence demands urgent attention. The documents and data are clear. The risk is real, and the window for preparation is closing.